Welcome to our capstone presentation. We are the Hearing-Impaired Conversation Isolator and Display Group. My name is Francis and I worked on this project alongside Dennea, Reynel, and Rachel. Our technical advisor and client for this project was Dr. Stephen Knudsen. Our project aims to address the communication barriers faced by individuals with severe hearing impairments. Many modern solutions to this problem already exist, like hearing aids or speech-to-text apps, which are available on most mobile devices. However, hearing aids struggle to be effective when the hearing loss is severe, and speech-to-text apps lack versatility and introduce privacy concerns, so we wanted to create our own solution. Therefore, the goal and expectation of this project was to create a device that is able to isolate voices, capture speech in real time, and wirelessly transmit this data to a smart device where it is translated into text. Our team spent the last 3 months working on a prototype using the resources such as the Elko Engineering Garage for 3D printing and open source firmware as the backbone of our project. The final prototype is a small, battery-powered receiving unit which uses a speech-to-text algorithm to translate the spoken words into text after a short delay. After the words are translated, a Wi-Fi connection is used to transmit the translated text to an easy-to-use iPhone app, where they can make the text bigger or smaller to comfortably read the text. Now, let's see a quick demo of our prototype in action.
Man, Grandpa, I love playing footsies with you in the locker room.
What?
Anyway, my capstone gala is coming up this Friday, and I need a thing to talk about for the...
Who?
My capstone gala is coming up this Friday, and I need a video to record for the capstone.
Francis, I can't hear you.
You never can, Grandpa. Don't you hate when this happens to you? I know I do. But thankfully, I think there's a product we could use. Whoa! No, Grandpa, no. We need this. My capstone gala is on Friday.
Oh, your capstone gala is on Friday.
Yes, Grandpa. See, you can hear me now. This is great.
Now on to the hardware side of things. There are 3 main components. All of them have a crucial role in enabling the functionality and performance of our device. We'll dive into each one. First up, we have the ReSpeaker mic array. This compact audio device is equipped with 4 microphones and is specifically designed for advanced sound processing and voice recognition applications. We chose this mic in particular for superior audio capabilities, which are essential for accurately capturing and processing the voice input. Next up, we have the Raspberry Pi 3B+. This powerful processing unit offers the high computing power needed for the speech-to-text conversion process in a compact and efficient form. We selected this unit for its compatibility with various software tools, making it the ideal choice to drive the core functionalities of our prototype. Last but not least, we've integrated a battery pack into our prototype design. This battery pack is essential for supplying power to both the Raspberry Pi and the ReSpeaker mic array, ensuring uninterrupted operation and enabling portability and rechargeability of our device. In summary, the combination of these 3 hardware components form the backbone of our prototype. The ReSpeaker mic array would capture and enhance the user's speech audio to then send it to the Raspberry Pi. The Pi would then process the audio received and convert it to text to then send it to our mobile application to be displayed.
So now let's talk about the firmware for our prototype. Upon startup, the Raspberry Pi runs a starting script which initializes a WebSocket and waits for a client to connect to it over Wi-Fi. Once a connection is established, the ReSpeaker begins listening for user speech. For our speech-to-text algorithm, we chose Deep Speech by Mozilla. Deep Speech is fully open source, which was perfect for our project's needs because then we'd be able to change it and modify it as we needed to. So we used their voice activation detection example code as the basis for our program because it already contained all the necessary code to begin capturing voice audio and translating it. We made some modifications, as you can see, to work with our WebSockets. Essentially, the program starts listening for audio input from the user, and as the user continues speaking, it'll keep taking in the information until there's a pause or a break in the user's speech. Once this break occurs, the deep speech algorithm will perform speech-to-text translation on this segment of speech and begin listening again. Mozilla provides a pre-trained model with their deep speech program, which we use. It's important to note that the model was trained to perform best in low-noise environments with clear recordings and has a bias towards US male accents. They also provide a scorer, which is what takes the spoken words and determines the most accurate text translation. Throughout our testing, we found that this algorithm was the most responsive and accurate. We also chose it over other considerations because it didn't need to be connected to the internet to work, which was an important factor early on in the design phase, due to a slow internet connection being a possible bottleneck when it comes to the translation process.
The primary software component of this project is the mobile application. Its main function is to provide a display for the hearing impaired to read the spoken text. So upon opening the app and ensuring that both the mobile device and Raspberry Pi are connected to the same Wi-Fi, the app will attempt to make a wireless connection with the Pi's WebSocket server. Once the connection is made, the application is ready to receive translated text from the Raspberry Pi. As someone is speaking into the device, the spoken text is promptly displayed onto the mobile device's screen. The app has a very simple user interface, including a scrollable text region, a green indicator in the top corner to signal the connection status, and users can also adjust the text size according to their preference by pressing the buttons at the bottom. React Native and Expo were used to develop the app due to React Native's compatibility with both Android and Apple, and Expo's ease of use.
In terms of what worked in our project, firstly, we completed the prototype in 3 months, and this device was able to translate audio data to text and display text on the mobile device interface. The interface was very user-friendly, and it is very simple to the seniors. We had the zoom in and zoom out features to help them to see the text clearly. The receiving unit is battery charged, and it actively captures speech data for 8 hours without recharging. The smart device is very easy to configure for the connection. It is automatically connected once configured. The speaker is activated by speech detection, and the receiving unit is light. The weight is only 400 grams, which is less than 500 grams weight requirement. It is portable and it is rechargeable. The product cost is only $157.17 Canadian dollars, which is less than 200 Canadian dollars requirement. In terms of what didn't work, firstly, the volume is 468.65 square centimeters, which is out of the size by around 1/5. Secondly, the noise suppression is not very well. It only works very well in a quiet environment. However, in a noisy environment, the translation accuracy drops. The wireless data transfer only works through Wi-Fi. It couldn't work through Bluetooth. Lastly, the receiving unit is not activated by the speech detection. It is always waiting for the audio inputs from the speaker. Only the speaker is activated by the speech detection. Let's look at the accuracy table. So the first column is the spoken sentence. We had one teammate to speak the sentence to the receiving unit. And the second column is the sentences that the receiving unit translated and displayed it in the mobile phone. We calculated the time translated per word, and then we calculated the translated accuracy. You can tell it from the table that the translated time is really fast. On average, it only takes half second per word to do the translation, and the accuracy is very high. On average, it's 90%. However, as I mentioned, this high accuracy, only occur in a very quiet environment. In a noisy environment, the accuracy drops.
There are several features that can be added to the prototype in the future to further optimize performance and usability. Currently, the application is only running on our local computers. In order to make the app more accessible, we will need to deploy the app to both the Apple App Store as well as the Google Play Store. To support Bluetooth, a Bluetooth Low Energy or BLE client will need to be implemented, along with any BLE functionality to replace the WebSocket client. Implementing features such as user accounts, conversation storage, and timestamps would enhance the user experience of the app, and in order to support these features, a database would need to be integrated to the system, in the backend, as well as any necessary APIs. And for maintainability of the app, metrics, logs, dashboards, alarms, and other error handling can be implemented just for a better development experience. And finally, if the device supports multi-language, then this is something that could be configured in the settings of the mobile app as well. On the firmware side, we can replace the WebSocket with a Bluetooth server. This would allow users to have access to the system in several environments, not just where there's Wi-Fi. Another enhancement would be to train our own model that is compatible with multi-channel mic setups and is capable of accurately capturing several languages and accents. A final addition to the firmware would be to incorporate more advanced noise suppression algorithms so that the device can be used in moderately noisy environments. Firstly, in terms of hardware, we can replace the Raspberry Pi with a more efficient system on a chip, since the Pi is equipped with many more features than what this project requires. One alternative is to use the ESP32-S3 microcontroller. This would ultimately reduce the size, weight, and power consumption while still providing the necessary processing power. Another addition would be to replace the battery pack with a power source that is integrated into the device. This would reduce the need for another USB connection and would also decrease the weight of the receiving unit. The final improvement would be to strip down the microphone setup of its extra features and work with the respeaker chip itself in order to reduce power consumption.
The Hearing-Impaired Conversation Isolator and Display prototype has successfully met its minimum requirements and its main goal of assisting individuals with hearing impairments in understanding spoken conversation. Despite coming across challenges along the way, the prototype demonstrates its ability to convert speech to text in real time and display it on a smart device. Overall, the project goal has been successfully achieved. We would like to thank Dr. Knudsen for his help and guidance throughout the term. We would also like to thank Eric and Jingjing for their guidance and feedback on our work. We also want to thank Steve Drake for his availability in the lab and his help as well. Thank you.